Hereby I open this academic ceremony in which Manlio Caldara will defend the academic thesis, Development of Molecularly Imprinted Polymer-based Sensing Platforms for Health and Environmental Applications. May I invite you to present a summary of your study and the conclusions of your thesis.
Thank you, Prorector, for the kind introduction. Dear members of the committee, supervisors, colleagues, family, and friends, welcome to my PhD defense. Today I'm going to introduce you my PhD work on the development of molecularly imprinted polymer-based sensing platforms for health and environmental applications. Firstly, I would like to start by introducing biosensors, their main components, and their working principle. Biosensors are comprised of two main components, receptor element and a transducer. The receptor element is responsible for binding a specific analyte in the analyzed sample. The transducer is responsible for translating this binding event into a measurable signal. During my PhD, I mostly focused on the receptor element and the transducer, mostly on optimizing the receptor element and the combination with the transducer. There are two main categories of receptor elements, natural receptors and synthetic receptors. Natural receptors, we can find enzymes, antibodies. In the synthetic receptors, we can find aptamers, metal clusters, such as metal organic frameworks, and polymers. As transducers, we can find different types of transducers. We can find electrochemical transducers, optical transducers, gravimetric, and thermometric transducers. The combination of these two is used in biosensor developments. An example of these can be found between enzymes and electrochemical. We can find here the very famous blood glucometer. Another example relies on antibodies with an optical readout, and this is very famous, very much used in lateral flow assays, especially in the immunosensors, such as the very famous COVID test that we've used a lot in the last years. During my PhD, I mostly focused on the synthesis, optimization, and development of molecularly imprinted polymers, and their correlation with two different types of transducers, thermometric and electrochemical transducers. When we started to think about our research, we started to think, where could we use molecularly imprinted polymer? Where could they be useful, in which field? So of course, we studied the literature, and the biggest field in biosensors is definitely glucose sensing. And glucose sensing is so important in different fields, such as food analysis, fermentation monitoring. But of course, the biggest application is in diabetes diagnosis and monitoring. The biggest biosensor used today is, of course, the blood glucometer. And this is used by millions of people every day. Diabetes is an incurable disease, and it has very important health concerns, but of course also economical burdens. We can see some numbers about diabetes. 422 million people live with diabetes in 2014. This number is seen to increase every year, and this disease is responsible of 1.5 million yearly deaths. And it's also a very important economic burden. So $237 billion are spent on direct medical costs for diabetic people, and $1 out of $4 in the US healthcare systems are spent on caring for diabetic people. So of course, it is very important to find novel alternatives to the commercial glucose biosensors, maybe better alternatives for some niche applications. Most commercial devices for glucose sensing are enzyme-based electrochemical biosensors. So they rely on an enzyme and on an electrochemical transducer. The enzyme is usually glucose oxidase or glucodehydrogenase, and in this case, the electrochemical transducer is called amperometry, uses a technique called amperometry. The main limitation of these biosensors resides on the stability of the enzyme. So indeed, the enzyme is not very stable at high temperature or extreme pressures. Therefore, the biosensor is not that stable in these extreme conditions. So molecularly imprinted polymers could offer an alternative due to their very favorable characteristics, such as resistant to extreme conditions, And therefore, they have a very long shelf life. They can be integrated with different readout techniques, and they have a low-cost synthesis, depending on the synthesis that you take. But what are actually molecularly imprinted polymers? Molecularly imprinted polymers are created with a process called molecular imprinting, when we use one or more functional monomers in order to create a pre-polymerization complex with a determined template. The pre-polymerization complex is then, by means of polymerization, used to create a polymer matrix where the template is embedded into it. At this point, we can extract the template, and then we will have a polymer matrix with cavities. Then these cavities will resemble in shape, size, and chemical functionality the template that we use to synthesize the polymer. In the next slides, you will see some examples where we will have NIP or non-imprinted polymers, and these are just reference materials where we synthesize a polymer as a reference indeed, where we do not add the target molecule in the mixture. In our first research work, we used a dummy imprinting approach, so we did not use the conventional method of molecular imprinting, but a slightly different approach, where you use not the exact same template that you want to analyze, but a different one. In this case, we used this molecule here, which is glucuronic acid. It's very similar to glucose, but it contains different functional groups. After optimizing these molecularly imprinted polymers, we then combined it with a thermal readout called heat transfer method, or HTM. In this readout, you basically are able to measure the thermal resistance changes or the raw temperature changes at the solid-liquid interface. After different characterization analysis, different rebinding in buffer solutions, our goal was to prove that we could use also this platform for biological sample analysis. And therefore, we analyzed human urine samples spiked with increasing concentration of glucose. And as you can see, our molecularly imprinted polymer was outperforming the non-imprinted polymer, so our reference, which proves that our molecularly imprinted polymer was specifically targeted for glucose. And as you can see, we proved that our biosensor could then be used for biological sample analysis of glucose. At this point, we used this fabrication technique to develop a molecularly imprinted polymer-based platform, and we started to research the literature to see where we could use some of the fabrication methods in this chapter. We analyzed different templates, and we came across this molecule here, melamine. This molecule, as you can see, it has a lot of nitrogen in its structure, and this molecule is usually used with resins in different products, such as different ceramics or different housewares. In the early 2000s, though, they started to find this molecule in milk samples, especially milk powder samples, but also milk liquid samples. But why did this happen? So when they analyze milk samples, when they want to analyze the protein content of a milk, they basically analyze with a method that is called Kildall method. They analyze the amount of nitrogen in the milk sample. If the amount of nitrogen is then correlated to the protein content of the milk. If you adulterate, so if you add some molecules that contain nitrogen into the milk sample, liquid or powder, you falsify the protein content of the milk. So you mimic protein-rich milk products. Of course, they did this, but this was with very serious consequences. And in 2008, there was a very important scandal, especially in China, where a lot of people had kidney stones, bladder cancer, renal failure due to this, and 51,900 kids were hospitalized only in that year in China. Of course, the regulators started to take action against the problem, and they put a legal limit of 2.5 milligram per kilos in milk and milk products. This in molarity is around 19.4 micromolar, and I will tell you more why we need to know this. So therefore, a lot of researchers started to develop novel detection methods for melamine. Of course, quantitative methods based on chromatographic techniques. This is basically the gold standard. method based on HPLC, GC, LCMS, very, very reliable, very sensitive, but they have disadvantages as well, such as high cost, they require trained personnel to use, and they are also time consuming. Therefore, researchers started to improve these methods or look for alternatives, and they started to make a lot of low-cost sensor kits based on enzymes, antibodies, colloidal gold, usually a combination of these. And the problem of these biosensors, though, is that they have a short shelf life. They do not give you usually quantifiable information. They either give you positive or negative. So they don't give you the exact amount of melamine in the sample. And they require reagents for labeling, which is not ideal for the end user, because they would need to use chemicals, which is also not ideal. So therefore, we started to think we could actually make novel biosensors based on molecularly imprinted polymers using some fabrication technique that we used basically in the other chapters. But in this case, to analyze a real-life sample such as milk and to analyze the melamine content in milk samples. Again, by using a combination of molecularly imprinted polymers with thermal readout technique. After doing a lot of characterization analysis of our platform and after characterizing in buffer solutions, we wanted to prove that we could have a food safety application with our platform. And therefore, we analyzed the milk spike samples. And the important thing about this slide is this graph on the right. You can see these lines, the black and the blue one. In the blue line, the melamine legal limit is depicted, which is 19.2 micromolar or 2.5 milligram per kilo, as I told you before. The very important thing that we achieved with our biosensors was our limit of detection was 3 times lower than the legal limit. So we proved that this sensor could be used as identification tool for melamine spiked milk. At this point, therefore we're able to make 2 different platforms for melamine in milk and for glucose in urine samples. And we wanted to improve another process, which is a bottleneck for MIPS. The problem is that when you deposit this receptor into a substrate, there are different deposition methods. And we used microcontact stamping, which is bottom left. We use this in the first 2 chapters. The problem of this method is that you use mechanically and manually, you put the molecularly imprinted polymers onto an adhesive layer. So it's not really reproducible because you do it basically by hand. And also you need different chemicals. We started to study different techniques such as screen printing, chemical and electrochemical deposition methods. And we came across screen printing, where you basically screen print an ink onto different substrates. We wanted to implement these on our molecularly imprinted polymers, and therefore we wanted to go from the fabrication process of microcontact stamping to the direct screen printing of our molecularly imprinted polymers. Therefore, the molecularly imprinted polymers for glucose were taken and screen printed onto a screen printed electrode, with different advantages. The advantages of this technique is that it's a single-step process, so you don't need to use a lot of chemicals. It's automated. Therefore, it's more reproducible. You can use the sensor as a dipstick, and you can also use it with a dual readout. Not only the thermal readout, but since you have an electrode, you can do electrochemical readouts. So we firstly characterize the screen-printed electrodes, of course, with SEM analysis. And then we could use this sensor for 2 different types of readouts, thermal and electrochemical. Again, we characterized the platform, and then we wanted to prove, besides buffer solution, that we could use this sensor for actual real-life sample application. And therefore, we, again, confirmed glucose absence in the urine that we were analyzed. And then we spiked the urine with increasing concentration of glucose to analyze the response. We were able to get some very nice rebinding analysis with thermal readout and electrochemical readout, proving that we could use a dual readout. So in conclusion, we were able to successfully synthesize MIPS towards glucose and melamine. We were able to make 2 different platforms for glucose and melamine analyzing real-life samples. And we were able to successfully integrate bulk glucose MIPS onto screen-printed electrode via using this new fabrication technique, screen printing. in the future, we would like to go towards the development of a MIP-based handheld wearable device for glucose detection. And we could use some of these fabrication methods to address novel and emerging pressing societal issues, such as antibiotics in food samples or PFAS, for example, in soil. Of course, last but not least, I would like to acknowledge all the funding that has supported us during these works, all the collaborators, and of course, my colleagues at the sensor engineering department that helped me a lot in these last 3-4 years. So I would like to give back the word to the prorector. Thank you for your attention.
Thank you very much for your very clear presentation. And let me welcome the audience here in the room and maybe also online joining through the live stream. Well, this is for me the opportunity to also introduce to you the supervisory team. They are not going to ask any questions according to Maastricht custom. So that is Professor Thomas Kley, Dr. Bart van Grinsen, and Dr. Casper Eersels. And my name is Ralph Peters. I'll be acting as the pro-rector today and guide you through this ceremony. Well, that brings us to the opposition. The opposition will be opened by Professor Oru. Professor Oru was the chair of the assessment committee and is also acting as the secretary of today's degree committee. He holds a chair in organic chemistry of bio-based building blocks at the Institute AMIBM of the Faculty of Science and Engineering of our university. Please, Professor Oru.
Thank you, Mr. Chairman, for giving me the opportunity to discuss with you, dear candidate, your very nice thesis. I thoroughly enjoyed reading it. There's a lot of different, let's say, aspects on it, which are not always organic chemistry. So I learned really a lot by reading it. But you will probably not be surprised that my questions will be more in the chemistry area. So I would like to at least go to you for my first question to page 16, which is in the first chapter, where you describe, let's say, the commonly used monomers for MIPs, which are all, if you look at them, fossil-based. Do you envision for the future, near or far future, also bio-based options?
Highly esteemed opponent, thank you for your comments and your questions. That is a really good point. Most of the meat production is right now made with mostly the first monomers that are tried is like methacrylic acid and acrylamide. I did as well that, but definitely I feel, especially seeing how the world is going, that the sustainable monomers are very much needed, and we should investigate a lot. I've seen a lot of papers in literature where they started to use chitosan or lignin to make novel molecularly imprinted polymers. The issue with that, I would say, is that there is not enough literature on it. So that's why also I didn't try to work on it, because I usually a lot of people in the field, they start to work, if you do free radical polymerization, they usually work with methacrylic acid and acrylamide. If you start to do electropolymerization, they usually go with pyrrole aniline. But after that, if you already want to try some different monomers, therefore you need to really dive deep into literature and also think a lot about the binding aspects of your material. I do believe that we should definitely investigate this. We didn't, but I do believe that it's definitely in the future something that people should actually consider even more.
Yeah, moreover, because if you look at the building blocks that are mentioned there and that you have used yourself, they are typically flat.
Yeah.
And you are sensing sometimes chiral molecules, like glucose, for instance.
Yeah.
So, and that was also actually a sort of question from me. How can you use a non-chiral, let's say, material to sense something chiral?
Yeah.
Because can you make then the difference between the D and the L glucose, for instance, or between glucose and another type of sugar, mannose.
Yeah. So thank you for the question. I really thought about that. And so when we started to design the first MIPS, basically, for glucose, I remember that we saw that in literature, there were a lot of studies on D-glucose with monomers. Okay, so I started working on it, but then at some point I started to think, well, why are we using the D? Yeah, and then I started to look online, and I discovered, after I started working on it, that D-glucose is also the most abundant in nature. So the L is more synthesized. So I would say we definitely use an high-chiral product, polymer, for a chiral molecule. Luckily, I was lucky enough to use the right molecule when I was imprinting. I definitely think that if you analyze the rebinding between the D-glucose with the sensor, whatever sensor, unless you have the enzyme, that case wouldn't matter that much. If you use polymers that have, our goal is to imprint the shape, size, and chemical functionality. So if you have the L instead of the D, definitely would have an effect. So if you imprint the D, and I imprinted the D glucuronic acid, but still D, so still with that conformation, I think if you analyze the L, will probably give you a lower D binding. Of course, I do not know. I know also that in literature, a lot of people are trying to, I don't know with how much success, but it would be, they are trying to analyze just an enantiomer, so making a sensor for one of the enantiomers, which I think is very, very interesting and very, very difficult. Because even in my sensor, you could see some cross-reactivity, and I think with molecularly imprinted polymers is almost always going to be a case that you are going to have some non-specific binding, which is definitely a problem, depending, of course, on the application that you have. But it would be very interesting to analyze.
Because I think it's interesting to understand how the, let's say, molecular recognition really works on a molecular level.
Absolutely.
Because then you could also use that knowledge to design, let's say, specific MIPS for other types of sensor applications. So what would you think is necessary to come to that stage that you would say, okay, I have here now, let's say, give an example, a neurotransmitter, maybe serotonin or something, and I want to develop a sensor application for that. Can you turn that around and then design the MIP for it?
Yeah. So
and how far are we from that stage?
Yeah, I do know that a lot of people, even some of our collaborators, are working a lot on computational chemistry of this, so to analyze the binding, geometry and behavior. And so I think you can definitely have a good guess if you have a good computational chemist, at least. And definitely if you make a chiral molecule, a chiral polymer for a chiral template, you would probably need to optimize it, but you would probably be likely to get very more specific binding towards that enantiomer. So I think it will be mostly a lot of computational which needs to be involved, but I think it's definitely possible, also not in that long period, I would believe. Okay.
Thank you. I'm satisfied, Mr. Chairman.
Thank you, Professor Oro. Then the opposition will be continued by Professor Wagner. Professor Wagner was a member of the assessment committee, and he also chair in soft matter and biophysics at the KU Leuven in Belgium. Please, Professor Wagner.
Thank you very much, and congratulations, dear candidate, on your presentation and your very colorful booklet. So I have prepared a couple of questions, and the first one would be, whenever you show a dose-response curve in your work, you always plot either the temperature T2 or the effect size. So why don't you print or plot the heat transfer resistance RTH?
Yeah.
What are the good reasons?
Highly esteemed opponent, thank you for your comments and your questions. That is a very, very good point. In my first work, which was the first glucose MIPS, I did most of the analysis with the T2, and then translated it into effect size in percentage. So basically, T1 minus T2, you know better than me, yeah. And so we basically plotted the dose response with percentage, and we did include, I believe, in our first research paper, we did include the thermal resistance as well to prove even more the rebinding capabilities of our material. I did analyze mostly the effect size because we wanted to, the HTM was, when I started 4 years ago, luckily a very well-developed method, and therefore I wanted to.
Okay, may I interrupt you?
Yeah.
Plotting T2 and effect size is perfect with me.
Yeah.
RTH has a little tiny technical problem. Do you know about it?
Yes, I do. Bart told me a lot. I did discover, actually, while reading one of the research papers from one of your old PhDs, that you could tune the PID settings, and I think that's what you meant. So by tuning the PID settings of your software, you will be able to have a faster response or lower, and then you could analyze basically more in the RTH or in the during the raw temperature.
But when you calculate it, the absolute value of the power is
you
never accurate because you have parasitic
yeah, because the temperature is
losses.
one of the factors.
Okay, let's proceed to the next question. When you analyze the urine,
yes.
So urine can have any pH value from pH 3 up to pH, I would say pH 8. Mm-hmm. Is the response of your sensors, the sensitivity, is it pH dependent?
Yeah, so thank you for the question. I did analyze firstly in PBS. So the first is in buffer solutions, pH 7.4, I think. And then I started to analyze with urine. I firstly checked the pH of urine. And we started firstly, we did not want to treat too much the sample that we used. The same for the melamine. We did not treat the milk because we think that if you treat the milk, you are adding basically one more step for the end user. So we did not treat the milk, and our urine, which was analyzed, was around a little bit lower than the pH 7. And since we got the rebinding capabilities, we were like, okay, we're satisfied with this, but you would definitely need to calibrate. We did not calibrate it with different pHs, but you would definitely need to calibrate it because the pH, as you said, of urine can be from a 5 to a 4 to 8, something like that. So I think it would have an effect. Probably not that big, but definitely could have an effect.
Okay, and you were speaking about end users.
Yes.
When you want to give a sensor to an end user, would you go for heat transfer or would you go for impedance spectroscopy as a readout principle?
I would go for the impedance spectroscopy simply because right now we do not have the HTM as portable device. I do think we could do that. I don't know how, because I'm not an engineer, unfortunately, but I do think that we could reach that level. But at the moment, the sensor that I've used for impedance in the last chapter of my thesis, I used a connector, but you could also have a handheld device for impedance spectroscopy. So I do think we could reach the level, but we are not there yet for the HTM. And instead, with the electrochemical spectroscopy, the potential stats now are very small. So you could definitely do it.
It's like an ID card. Can you give an estimate how long it will take until you can buy one of your sensors in a pharmacy?
Well, I do believe that there is still a lot of research that needs to be done. I do believe that definitely selectivity needs to be assessed much more. pH needs to be assessed much more. What we wanted to do, I think, brought us a bit closer because we not only wanted to do rebinding analysis in buffers, but we did wanted to go for the proof of application.
Yeah.
So I think we are closer, but still a lot of optimization needs to be done.
So this research or this approach, I think, is covered by several patents, and one day they will be outdated, so get it on the market before.
Yeah.
And now my final question, and I would need assistance by the para-nymphs. It's regarding the propositions. Proposition number 7, maybe you can read it.
Of course. Highly sensitive and selective does not always mean better.
Yeah. Okay, thank you. So when I was reading this proposition, I thought first maybe the candidate is talking about people, that it's not good to be too sensitive and to be too selective in what you are doing. Do you mean it about people or about your sensor?
No, I meant it about the sensor. And so what do I mean with this proposition is that I've seen a lot of research where they try to go as low as possible, which is very good, which is very, I really appreciate that. But I do think that, and that's what we try to do in all our works, that when you do something, you need to do it for a reason. So when we started to go with our sensor, we knew what LOD we wanted to reach, and we didn't set a goal. There is no point in having a glucose sensor that goes to nanometer scales when in blood you have 5 millimolar of glucose. So I do think sensitivity and selectivity are definitely, and this is for sensitivity. For selectivity, I would say that is definitely important, but it also depends there. Because if you are analyzing, for example, different drugs of abuse, it's better if it's less selective, so you detect the whole drug, the whole class of drug, instead of detecting only that drug, and then you would lose a lot of other molecules.
All right. So thank you very much.
Thank you.
I'm finished.
Thank you.
Thank you, Professor Wagner. Then the opposition will be continued by Professor De Verme. Professor De Verme was a member of the assessment committee, and he holds a chair in engineering materials and applications at Hasselt University, also in Belgium. Please, Professor De Verme.
Thanks, Pro-Rector. Dear candidate, let me first congratulate you with a very nice thesis. It was a pleasure to read it, and also with the very nice presentation. Now it gives a very clear overview of what you've written in this booklet, so congratulations on that already. Let me start with a very open question that links a bit to the colleague, Professor Wagner, on what you said about stability of enzymes and then the MIP sensors. You say they are more stable, so they are, let's say, the future, but why are they not on the market yet? You mentioned a bit already on let's say, selectivity, but can you elaborate a bit more on other aspects, why we don't see them on the market yet?
Yeah, I esteemed opponent, thank you for your comments and your questions. There is a question that I've asked myself a lot as well in these last years. I do believe we are getting closer, and the thing is that the enzymes have been developed a lot, especially for glucose. They have had years developing glucose oxidase, glucose dehydrogenase. They've been implemented into a lot of biosensors. Now they are going for amazing innovations with the continuous glucose monitoring and others, and also all other applications. I do think that MIPS could be very, very interesting for a lot of different applications where enzymes lag. In my presentation, I pointed out the stability of the enzyme. Now, to be completely honest, the enzyme of glucose works amazingly. Glucose biosensor is the most used biosensor every day, so nothing to say about that. But the problem is, and we, for example, we were approached by a company that actually read our work, and they were interested in our sensor because they did have a specific niche application. So they wanted to measure glucose in tomatoes, and they were not able to do that because of the PA. I mean, they were able to do it with the different types of enzyme, with the hexokinase instead of the oxidase. But the oxidase, which is commonly widely used, is usually not that, doesn't work that well at acidic pH, and we were giving them probably an alternative for analyzing that. Saying that, the problem with molecularly imprinted polymers and commercialization, I think, first of all, there are some commercial, they sell either the columns with the molecularly imprinted polymers embedded into it, like HPLC columns, but they do not sell right now. Nobody sells a biosensor based on the molecularly imprinted polymer. I do believe that there is still a lot of research that needs to be done. And especially the deposition process, for example, we did analyze that, and we noticed with my colleagues, we noticed that nobody has ever done that, which is, to me, mind-boggling, because we were thinking, this is basically one thing that everyone needs to do if they want a biosensor, and everyone does whatever they want. Everyone decides on one method instead of another. For example, antibodies, there are specific protocols that everyone has to follow, EDC and HS coupling, for example. And in our, with the molecularly imprinted polymers is basically the Wild West of deposition methods. So you can choose whatever you want to choose. So I think we need protocols. I think we need definitely a lot of optimization. And unfortunately, we will always have some, depending on the synthesis process, we will always have also some inter-batch variability in the molecularly imprinted polymers, especially if you do bulk polymerization, I would say, which is what I did. But if you try to do different techniques, I think you will probably improve that. But I do believe that you still need a lot of research in the next years.
You talk about deposition. That is perfectly leading to my next question.
Yeah.
You in chapter 5 you nicely described different deposition techniques. You used screen printing in chapter 6. If you have to conclude from chapter 5 linked to your work in chapter 6, what would be your proposition of deposition technique? That is, let's say, if you go to the market, you need mass production. So, which technique do you think would be the best technique to do that, to reach that level?
I do think the screen printing is very strong. I do think the screen printing, especially made in a mass production, stencil. You know better than me. I think that is very strong, but the problem is then the deposition that we used is also, we screen printed on top of the screen printing electrode, which is still one step more. I do think screen printing is very strong, but my best guess at this moment, also seeing especially antibodies, for example, I would say is mostly grafting and covalent binding to the surface, which I have not done myself. Some of our colleagues did. I think if you manage to get grafting, to graft your polymer into a surface in a very reproducible manner, that could bring you very close to the marker.
Because let's say, if you look at screen printing, you say you screen print directly onto the electrode.
Yeah.
Did you test, let's say, their stability and adhesion of your MIPS on the electrode itself? Did you test that?
I did it qualitatively test, so I was going to the SEM basically a lot, and I was analyzing basically the MIP surface, not the MIPS, the screen printing surface after each rebinding. We did not do the screen printing ourselves because we do not have the machine to do it. With some other collaborators did, but they have a lot of expertise on it. So that's why they also usually do a lot of different percentage of polymer in the ink, basically. And they did optimize that, and therefore there are other MIP-based SPEs that have higher or lower polymer percentage in the ink. In our ink, it was 5%, but I did not test the stability of it. I did test visually, basically, with electron microscopes, how we would look first, before and after rebindings, basically. And I did find, if I can say that, I did find that the screen printing on the screen printer was much more reliable after the measurement than the micro-contact stamping. Of course, micro-contact stamping, I do it by hand, and it is in an adhesive layer. And when you inject basically some powder, I think it might fly away if it's not properly deposited. We try to avoid that by analyzing a lot when we try to do the stamping. But yes, as best as we can. I do think the screen printing brought us much closer to an actual product.
Yeah, but I still think that some investigation there is needed in, let's say, the adhesion of what you print onto the electrodes, because with stamping you really, let's say, push
on
your
top.
MIPS in, let's say, more or less inside or partly inside, which probably is not fully the case with the screen printing process. But that's something that that then the colleagues, I think in Manchester, should elaborate further on. So if we go to the thesis, I have a question related to the printing itself, or let's say the transducer techniques you used in chapter 6.
Yeah.
But in figure 3.13, you show that you measure glucose, but also fructose, sucrose, and lactose. And what you see that, for example, for the sucrose, it follows more or less the level or the effect size of glucose up to a millimolar of, let's say, 0.1, 0.12. Then it drops down. For the blue one, the lactose, you see that it stays low first, but then it goes up. Can you explain that a bit? What is happening there?
Yeah. I've actually wondered as well. And this is in urine, yes. So this is in human urine samples. We did the same analysis in buffer, and we got like kind of similar results as well. But yeah, so what we formulated that could be an hypothesis of this is, so we analyzed 3 different carbohydrates. And the fact is that sucrose and lactose, so lactose is a disaccharide, and it's formed by glycosidic bond between glucose and galactose. And the sucrose is, sucrose is actually 2 glucose units. So we thought that since when we make the cavities, we basically imprint almost a glucose molecule, a glucuronic acid, but almost a 6-member ring. We think that there is some partial binding between the sucrose, for example, and lactose, which also have 1 glucose ring. That's why we think we see some partial response. And indeed, that was also like kind of proven by the fact that fructose instead has a lower effect size, because it is very similar functionality-wise, but it's a pentose, so it's being smaller, probably it does not interact very well with the pocket that we made. And that was our best explanation of this.
Okay, and then maybe one quick question related to that. Suppose you have 2 of them, glucose and sucrose, together, and you would like to distinguish both with one sensor. How would you do that? How would you target that?
Glucose and sucrose.
Yeah, or other ones. Does it matter that much?
No, no. I don't think it does matter that much. I think you would need to go back to the lab and try to optimize again the new ration. My best guess would be to make another MIP with using a different template at that point, and probably optimizing it with the help of computational chemistry, I would say.
Maybe as a follow-up research, it would be interesting not to focus on the sensing element, but on the readout, the transducer element. And you used in chapter 6, you used impedance measurements, but also the heat transfer method. Yeah. Maybe you can combine both to measure the difference between the glucose and the sucrose, for example.
Absolutely.
So think about that.
That could be very good. That's a very good suggestion.
Okay, thanks a lot.
Thank
That's
you.
one of my questions.
Thank you.
Thank you very much. I think there's food for thought for during the reception. You can continue there. The opposition will now be continued by Dr. Baker. He was a member of the assessment committee, and he's an assistant professor of complex tissue regeneration at the Merlin Institute of the Faculty of Health Medicine and Life Sciences. Please, Dr. Baker.
Thank you, Mr. Prorector, and dear candidate. Lovely thesis. Congratulations to you and to your advisory team for this nice body of work. I'll start off with a proposition, so I'll ask for one of your paranymphs to help me out here as well and read proposition number 5.
Chemical sensing technologies drive innovation and optimization across industries.
And I'll ask you to explain to me more what you mean by that. It's quite a generic sentence, and I don't know if I fully agree.
Hi, esteemed opponent. Thank you for your comments and your questions. It's number 5, right?
Yeah, so can you give me, maybe just give me an example of where chemical sensing technologies drive innovation and optimization across industries? What's a good example of that?
Yeah, an example could be, for example, the glucose sensor. It could be an example. You use enzymes, yes, but I would say.
And what industry is the glucose sensor changing? What industry is the glucose sensor changing?
Well, the healthcare industry, I would say, mostly.
Right.
And yeah, of course, all the economics behind the healthcares around the world, they would be definitely affected by it, I would say.
Okay, so I would argue that it's not necessarily chemical sensing technologies that drive innovation, but what about spectroscopy methods? Yeah, I agree that chemical determination is there, but would you disagree with me that it's actually more spectroscopy that drives it, or sensing?
No, I do agree with you. There is more spectroscopy. For example, I'm thinking about the drug tests that they do at the airports. I do think they use FTIR, I guess. I do think they use FTIR, so I would say definitely spectroscopy used.
Or small mass specs,
or small mass
specs,
there, which have been developed a lot now.
But then what I want to hear from you, because I view it this way, you view it that way, we sit on different sides of the fence, but we're talking about the same thing. Where do you draw the line between what is chemical sensing, what is spectroscopy? When do I use one, when do I use the other? How do you view that after doing a PhD in it?
Yeah, I would say that is a difficult line to draw.
Could you do it in a few sentences for me, the best you can?
I would include spectroscopy into the chemical sensing technologies.
Okay.
And that's why I did write it.
Fair enough, understandable. Now to dig into the science a little bit more, you won't be too surprised, Chapter 3 resonated quite well with me, and I found it super interesting, but also conceptually it troubled me a little bit, this pro-binder approach or whatever, where you use gluconic acid instead of glucose. Why in the world would you optimize for something that you're not trying to measure? What was the thought process there?
I will be completely honest with you now, and I will tell you why I did that in very plain words. Because I started my PhD in 2020, and I did start to try imprinting glucose, because that's how imprinting works, ideally. So I imprinted glucose and then doing rebinding of the materials. The problem also that really made it a bit of a struggle, that glucose is not UV active. So usually what we do is UVPs. So basically we do a calibration curve and then we analyze the rebinding after the incubation. With glucose that was not possible because it's not UV active. So I was doing a lot of LCMS, which I learned a lot in that period. And so ideally, I wanted to, the plan was to imprint glucose and rebind glucose. Then my colleague had a very good suggestion, and we thought maybe, and it did not work at all, right, for 1 year or so. So I was trying to change a lot of the composition, to try different monomers, a lot of different monomers. And it did not, basically the rebinding efficiency was not that good. Okay. And we did try with glucuronic acid as basically safety net before moving on to something else. But when we tried with glucuronic acid, we tried with glucuronic acid and acrylamide. We thought, I also found a paper which I can show you.
Let me try to wrap this up. It seems like, was it just a bit of a good stroke of luck, or was it a rational choice?
No, it was a stroke of luck.
A good stroke of luck.
Yes.
Okay.
And honestly, and then I started to think why that happened, because I would wonder as well, why would it work?
Well, I'll get us there. Don't jump there quite yet.
Go.
So the first thing I want to ask, though, is also, I didn't see in your thesis, and I don't know if you did it, but did you ever measure the response to gluconic acid?
Yes, I've never done that, and I have a reason for that. I've never analyzed the glucuronic acid. We did think, why would we want to measure glucuronic acid if we want to make a glucose sensor? of course, for sake of selectivity, you would do that.
Yeah.
It's not very common to do it when you use a dummy. Dummy polymerization is usually used when the actual template either is very expensive, very toxic, mostly these two reasons, but which is not the case for glucose.
But then why did you not do it?
Yeah, the idea was like, why would we do it if we want to measure glucose sensor? But then I discovered that glucuronic acid is actually present in urine, in low amounts. And luckily, though, glucuronic acid is more stable than glucose, or at least there is not enough research to support otherwise, that glucuronic acid is not, doesn't change as much as glucose change. But yes, we did not try.
Okay, clear.
Yeah.
And then I had one more. Your background's pharmacology, right?
Yes.
So
pharmacy.
Pharmacy. So I think you know the lock and key approach, that the environment and the binding play an important role.
Yeah.
I would say that the materials that you make are quite simple at this point, but also the way you make them, they're kind of a hydrogel, right?
The materials that I make.
Yeah, they're kind of a hydrogel, no?
No.
No? Why not? Why not?
So the polymer that we made, they are bulk polymers, so very hydrophobic, I would say.
With ethylene glycol and acrylamide?
Yes, but they are highly cross-linked, and so we get a bulk a bulk piece of polymer, which we then crush and sieve.
Right. But if we're running short on time, so I'll push this along quickly, but you do this bulk polymerization in DMSO, right?
Sorry again?
You do this bulk polymerization in DMSO, correct?
Yes.
Right, and then you remove the solvent. So you do have a swollen network there that comes into contact with water. So I'll say that, they're not really a hydrogel, but somewhere in between. But how do you think you've got dummy interactions? You've got you do your MIP in a different environment than your sensing environment, where you make the MIP in the DMSO and then you measure in water. In 2 or 3 sentences, you use simple polymers. If you had $1 million now, and then you say you're running the next research group, you have to make 3 improvements in your sensor. You can only change the polymer or the processing. What would you do?
So I can only change the polymer or the processing?
Yeah. You can't change the sensor. You can't change the deposition method. You have to change the chemistry. What would you do?
I would definitely change the polymerization process.
Okay.
I would probably go for something that is well known to be more homogeneous.
Okay.
For example, I would think about emulsion polymerization.
Okay.
Also because I know that bulk polymers have very high variability batch to batch. So that what I would change is mostly the polymerization process.
Okay. It's good enough for me. Thanks.
Thank you.
Thank you very much. I guess more food for thought at the reception. Then we'll move on to the last opponent. That will be Dr. Lopez Iglesias. She's a member of the assessment committee, and she's an associate professor in microscopy and life sciences and structural cell biology at the Faculty of Health Medicine and Life Sciences at this university.
Thank you, Prorector. Yeah, dear candidate. So the first thing that I would like to do is to congratulate you very much and your promotion team because of this work that is excellent in my opinion, and also that allows me to read it and to understand. I am really out of your field, and I thought that it would be not possible for me, but it's so well written and so well explained that I was able to understand a little bit at least, but yeah, and to have some questions from there and to arrive to some conclusions and to learn a lot. So congratulations. But my first issue is with your title, because you are constructing biosensors of glucose and melamine, right? And you talk about health and environmental applications. Is not all about health, or we can consider melamine in milk like something else?
Yeah. Highly esteemed opponent, thank you for your comments and your questions. They are laughing because I told them that I made a mistake in the title. And I have a slide for that. and I will take it. So what I do believe that I could have changed in my title is for health, of course, is mostly the topic, but I would change environmental with different kind of fields, because in the end, at the end of the day, melamine is mostly found in food, right? At least, unfortunately, is mostly found in food, and so I would go mostly for example, for food safety applications. Why I changed that to environmental, and I will go to the end, and then I will go back. Yes, and so I thought, like, why can we think about environmental applications? So I started to read a lot of literature when I was doing when I was writing the thesis, when I was choosing the title, and it is true that we have done only food safety applications for melamine, because we basically analyzed in milk. We did the buffer solution in calcium chloride, which mimics milk. But we did then think it could be used as an environmental tool, because this platform that we made could be used, for example, here they analyzed in animal tissues and products, or even in swimming pool water. I do agree still, it can fall still under the health umbrella, I would say, the health applications umbrella. But absolutely, it could be also environmental. And I do understand also they could be called food safety. So I would either I would have to choose one. Yeah.
Yeah, it's more about the potential applications also.
Yes.
Right?
Yeah, indeed.
Yeah. Okay. So yeah, I have something about microscopy, of course, because it's, as you know, my field. I know that you learn with us about microscopy, but I have a little bit. Not complaints, but maybe complaints to myself also, because I am seeing that, how the images are treated are not really the best, but I am seeing something. It is the difference from the chapter 3 and 4 to the 6. So it's because it's chronological done, and was chronological done, and you were learning in this trajet, or because you in the 4 chapters you are including the SEM images in the material and methods, but not only the method but also the results. And then in the last chapter, chapter 6, is like I will say correct, because you mentioned the technique in the material and methods, and then the results together with your results of the biosensoring, or the results that you are aiming for. But in my view, to do the characterization or validation or any other,
absolutely,
through microscopy is also a result. Yeah, correct me if
I
I'm wrong.
completely agree.
Differently.
The reason is just, as you mentioned, is just the timeline. So when I started my PhD, we were not in Maastricht, and I did not know that I could measure the SEM at your institute. And I did try to do, indeed, in the chapter 3, my biggest characterization analysis, I would say, of the surface was unfortunately just microscope. I don't know if you saw it, which is, I guess, it's just a light microscopy. And then from melamine onwards, in the chapter 4, this was included in supplementary simply because we did not have the time, and I did not include it in the original manuscript. Then the reviewers asked for it, and we did include it as an addition when to respond to some reviewers. But I do agree completely that that it is needed, and it is very good results that shows a lot of their characterization, and that's why at the end I included it in the results, because at the end I knew I could do it, so I knew also how to characterize it.
Yeah, in chapter 6 is very correct in my opinion. So going to some details, in chapter 4, in the page 106 and 7, so you do the EDX analysis.
Yes.
So I would like to clarify that the EDX analysis refers to you elements. It's an elemental analysis, not chemical. I mean, you just detect elements.
Yes.
You don't know about the molecules that they are formed.
Yeah, indeed.
Yeah? Okay, because it's written chemical properties, maybe you can change for the next...
In 100?
106.
Yes, you are completely right.
It's just a clarification.
So what we wanted to prove with the EDX was just, this is a bare aluminum layer, and in A and in C you see the layer with the polymers. So what I did with the EDX in your institute was I was analyzing, of course, only the surface, and therefore we see the aluminum a lot, of course, skyrocketing. And in C, we covered the aluminum, and then we added the polymers. So we saw, that's why I wanted to highlight the carbon and the oxygen of the polymer.
Yeah, again, in this C, I am curious why you are not detecting aluminum.
I did go only on the polymer particle, which is on top of the...
The thickness doesn't allow you to go deeper.
No, because the D, so the EDX analysis is only on the polymer particle, not in the surface of the aluminum chip.
Okay.
That's why I didn't see the.
I will appreciate some arrows in your images. We used to put arrows to just to indicate where the particles or any other thing is. Yeah, but these are formal things, but I like to educate also in my field. But I have a question that I am curious about. Imagine that you get a droplet of water that is infected with some viruses and bacteria, and someone asks you to use one of these devices to detect which kind of virus are there or which kind of bacteria. What do you envision that you could do with the current technology?
To detect the bacteria.
To detect which kind of viruses and bacteria, and to discriminate among them.
Yeah. So my parent did that during the PhD.
Oh,
so yes. So there is another type of polymers that we use, which is called surface imprinted polymers, and they basically are mostly a layer, not with the polymer pre-made and put it on the layer, but it's just a layer where you imprint the bacteria. It's usually done with bacteria and not with viruses. Viruses are too big, and then you rebind the bacteria.
Manlio Caldara, the time appointed for defending your thesis has passed. The degree committee will now withdraw to discuss the quality of your thesis and your defense. I request that you and your company, that's the audience, await the results of our deliberations and our return in this room.
The PhD defense has now ended. The degree committee will debate the candidate's performance behind closed doors. This process usually takes about 10 minutes.
Long road to the south side. 7 miles in my rearview mirror, I know what it felt like. My goal's only getting clearer, east side to the west side. No place like home, if it's questions that you've got, go the extra mile and die. All your time, 'cause I'll go the extra mile. Long road to the south side, 7 miles in my rearview mirror, I know what it felt like. My goal's only getting clearer, east side to the west side. No place like home, if it's questions that you've got, go the extra mile and die. On the dash, got my laces tied. Long road, I don't waste no time. Break rules because fate decides. With the team and we chase the light. I make a move, fall down, shake it off. I hate to lose, bad branch, break it off. No room for negativity, praise and love. Prepare for deep part cause we're taking off. Get the mileage, traveling so far from home. Gathering knowledge, other connections. I put the time in to get everything I ever hoped for. It's a challenge and we all in. It's a better future that we go for. And even though these nights seem long, I know that I am never on my own. Know you've won the battle once you've grown. Long road to the south side, 10 miles in my rearview mirror. I know what it felt like. My goals only getting clearer. East side to the west side, no place like home. If it's questions that you've got, go the extra mile and that. Long road to the south side, 10 miles in my rearview mirror. I know what it felt like. My goals only getting clearer. East side to the west side, no place like home. If it's questions that you've got, go the extra mile and that. What's on the line? I know you know that I can't read your mind. Years can't fly by now, don't waste all your time. Cause I'll go the extra mile.
Let me reopen the session. Manlio Caldara, the degree committee here present has assessed the quality of your thesis and your defense. And in view of its positive verdict and taking into account your previous qualifications, the degree committee has decided to grant you the degree of doctor. Professor Klei is authorized to confer upon you this academic distinction in accordance with Dutch university custom. I invite your supervisor to now take the floor.
Do you promise to work in accordance with the principles of scientific integrity at all times, to be careful and honest, transparent, independent and responsible?
I promise.
By the authority vested in us by law and in conformity with the decision of the committee here present, I hereby confer upon you, Manlio Caldara, the degree of doctor and grant you all rights attached by custom and law. As evidence of this, I now present you with a degree certificate signed by the rector, the secretary and the other members of the committee and affixed with the official seal of the university.
Congratulations.
As is custom in the meantime, I think most of the people here know that I'm the dean of the faculty, and as such, Manlio started when I was already dean, and I'm still dean of this faculty. So actually, the real honor of supervising is not mine, but it's in the gentleman here to my left of me. So yeah, I'll ask Bart to speak to Laudatio. But very much congratulations.
Thank you.
Thank you. Dr. Manlio, 100% Caldara. You're almost done, but in true SE tradition, you have to endure a few words. It was interesting to follow your journey. You started your journey with us roughly 4 years ago, about a week before the first lockdown. All of a sudden, a shy guy from Palermo found himself in a lockdown situation in a country where it rains 87% of the time and where supermarket noodles can pass for pasta. Your direct contact with SE consisted with the daily morning app, Everybody Good, followed by a very personal thumbs up. But everything comes to an end, even this era. And it was after this that you really got started. You did not have a lot of lab experience, you were shy, cautious, and fighting to get that first MIP. Sorry. getting old. Let me see. Sorry. Now you were there. You were going to publish that first paper. You were so close, almost ready to submit. And then, no kids around, we found out that we got fucked over. Someone published your idea, your paper. As disappointed as you were, I believe this was your defining moment. It transformed you into the researcher and maybe even the person that you are today. A situation like this can go south really fast, and it almost did. You came into my office with sheer disappointment. But I think it was at this moment where we discovered Manlio 100% Caldara. Disappointment turned into anger. Anger turned into determination. You grew some academic teeth and were not afraid to enter an academic bare-knuckle fight. You started drinking liters of water and then produced liters of urine. Uncountable flasks were filled, many flow cells were soiled, and people were afraid to bump into you into the hallway. But you were gonna get that paper. And then you did. Your first big paper. Looking back, it is not the paper which is the most important here. It was your transformation. You found out that you were a fighter. And after this, there was no stopping you. That shy boy from Palermo, who did not have a lot of experience in the lab, now owned the lab. Ample ideas to pursue, people to inspire, and Scopus was your starting page. We created a monster. But these long days in the lab took its toll. We tried pumping the brakes a couple of times, but you went on and on. In no time, you wrote up your thesis, but a few bumps in the road hit you hard. For a while, I saw that shy Palermo guy again, and it took a while to find Manlio 100% Caldara. However, after a while, I saw him again. You started to inspire people in the lab again. You started to write again. You started pumping yourself for today. And now here you are, Dr. Manlio Caldara. You did it. You're done. Sadly, your AZ adventure ends here. We will miss your infectious enthusiasm in the lab, your hunger for papers, and your willingness to fight and to do whatever it takes. If anything, I hope that this is what you will take from this journey. You're a fighter. Dear Manlio, thank you for being part of AZ. I wish you nothing but success in your future endeavors, and I hope you will check in every once in a while. Congratulations.
Thank you.
Dear Dr. Caldara, also on behalf of Maastricht University, I would like to congratulate you with the degree you have acquired, and I would like to extend my congratulations also to the family and friends, and the colleagues and everyone present here or online. And yes, let me also thank, by the way, the committee members for all the effort they put into this thesis, and I hope you enjoyed today's defense as much as I did. Yeah, that brings us to the end of this official part of the meeting. Let me close that. And there's a few household messages. Now that we're at the end, we're going to make some pictures with the opponents and of course, the young doctor, the paronyms, on the stairs. And then there's going to be a brief moment for us to congratulate, because the reception is going to be right outside of the building, down the little hill that we're on. At Que Pasa, so we will probably go there together. Thank you all for joining, and hope to see you in a minute. Yeah.